Hello, this is Math 2115 coming to you from the College U page, and the title of this lecture is Proofs by Mathematical Induction. Be an active listener as you watch these videos. You just saw a video where a bunch of dominoes were being knocked down, so now I'm going to ask you to imagine or visualize the idea of an infinite collection of dominoes. We saw 32,000, but these are going to be infinite, way more than 32,000. But they're positioned one behind another in such a way that if any given domino falls backwards, it makes the one next to it fall backwards. So here's what happens. You tip this one over, it drops all these over, and for every integer k, if I knock over the kth one, the k plus first one, dot, dot, dot. And so what happens is all fall down. But here there were an infinite collection of dominoes. They all fall down. That's the idea behind the principle of mathematical induction. Let P of n be a property that is defined for integers n, so n is here, and let a be a fixed number. Suppose that the following two statements are true. P of a is true. That means you're knocking down the 8th domino. You're starting somewhere. You're knocking something down. It is true. And for every integer k bigger than or equal to a, whenever P of k is true, then P of k plus 1 is true. That means the truth of this one forces the next one to be true. Then, if you have both of these conditions, then the statement for every integer n bigger than or equal to a, P of n is true. And that means you've proven this for an infinite number of integers. This is pretty heavy, so think about it. And here's operationally how you go about doing a proof by induction. So you consider a statement of the form for every integer n greater than some starting point, a property P of n is true. To prove such a statement, you do the two steps. You show that P of a is true. You have to show this, and this is called your basis step. Then you do the induction step. Show that for every integer k bigger than or equal to a, if P of k is true. So you see, this is the if part that we've studied. So this is a hypothesis. Then the conclusion is P of k plus 1 is true. So we assume that P of k is true, where k is any particular but arbitrarily chosen integer k bigger than or equal to a. And this is called the induction hypothesis or inductive hypothesis. Then show that P of k plus 1 is true. Examples are much better than theory, although I think it helps to think about the dominoes. So let's use mathematical induction to prove that 1 plus 2 plus dot, 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 all the way up to plus n is equal to n, parentheses, n plus 1, n times n plus 1, all by 2, for every integer n bigger than or equal to 1. So we're starting at 1, and this is P of n. This is the statement that we have to prove. There is value in trying to see if you know what to do. So look at what we did before and give it a go. Let's see how you did. So this is the property P of n that we're trying to prove. So this is P of n. We have to show that P of 1 is true. So if we just take one term on this side, we get just 1. And if we put n to be 1 on the other side, we get this, which ends up being 1. So 1 is equal to 1. So P of 1 is true. Now we're going to show for every integer k bigger than or equal to 1, our starting point, if P of k is true, then P of k plus 1 is also true. So now this is our inductive hypothesis. We're going to suppose that for any integer k with k equal 1 bigger than or equal to 1, such that the first k integers are equal to k times k plus 1 over 2. You see, we're letting n in the formula be k, and we're assuming that that is true. Suppose it is true. Then we must show that p of k plus 1 is true. And that is, we have to show that if I add one more number on this side, I will get the other side where it's k plus 1. So instead of having n is now k plus 1, n is now k plus 1 over 2. And so this is what we have to show. But when we're thinking about the algebra, we have to realize that k plus 1 is k plus 2. So if we got to this point, then we could just say, but this is equal to that. So that's what we have to show. Okay, so let's take the left-hand side of pk plus 1, which is going to be this part. And so it's 1 plus 2 plus 3 plus ... plus k plus 1. Now, this blue part is our inductive hypothesis. So we're going to be assuming that that is k times k plus 1 over 2. So the blue part is that, and now I'm adding 1 to it. But now I'm going to get a common denominator. And when I get the common denominator, this one I have to multiply top and bottom by 2. So I'm going to have k times k plus 1 plus 2k plus 1 all over 2. Now I'm going to leave the 2 down there, but when I distribute this, I will have 2k plus 2. And when you add the things, I'm just going to leave that 2 in the common denominator, but now I'm going to have k squared plus, there's 1k, there's 2k, that's going to be 3k plus 2 over 2. That's just algebra. But this is the same thing as, you can factor that numerator, and you get it's this. And we said that was good enough because this is equal to that. So you see, the two sides of pk plus 1 are equal to the same quantity, and they're equal to each other. Therefore, the equation p of k plus 1 is true, as was to be shown. Therefore, by mathematical induction, this is true for every n. If a sum with a variable number of terms is shown to be equal to an expression that does not contain either an ellipsis, that is the ... or a summation symbol, then we say that the sum is written in closed form. Now, the reason I introduced that is because that's in this example we're going to do. So let's apply that formula that we just learned and that should be committed to memory to evaluate A and B and come up with a closed form for this sum. You know what to do. Let's see how you did. Okay, here, and again we have a formula for the first n digits, but this is 2 plus so on and so forth. But I'm just going to factor a 2 out of all of those numbers. It's going to be 2 times, and this is the numbers added up from 1 to 250. Now we know this is going to be, n is 250, so it's 250 times 250 plus 1 over 2 times 2. The 2's will cancel. When I take this number times this number, I get this number. That's the answer to that one. Here, I'm starting at 5 instead of at 1. So what I'm going to do is a great mathematical technique of adding and subtracting the same thing. So what I'm going to do is I'm going to take the sum from 1 to 50, but then I'm going to subtract off the first 4 terms. Well, the sum from 1 to 50 is, and so here it is in our formula is 50 times 50 plus 1 all over 2. But then this I'm subtracting off, so this is going to be 10. So I do this calculation, subtract 10, and I get this as my answer. Here I'm adding the numbers 1, 2, 3 all the way up to h minus 1. So the n is h minus 1. So this is h minus 1 times h minus 1 plus 1 over 2. But this will cancel. This is h over 2, and there is a closed form formula for that. Let's do another example, and we're going to prove that this formula is true for R and any real number r, and we're going to r is not 0. And we're going to prove that this is true for any real number r not equal to 0, and we're going to use the principle of mathematical induction to do it. So this whole statement is P of n. You know what to do. Let's see how you did. So this is P of n. That's what we have to prove, is if we add up all those numbers, we get what we want to have. Okay, so we're going to start, and we're going to see what happens if we take P to be 0. Well, if we take P to be 0, what we're doing is we're putting n to be 0 in the formula, so we're summing this, and what we will get is 1. And on this side we get r to the 0, which is also 1. So P of 0 is true. Now suppose for every integer k bigger than or equal to 0, if this is true, we're assuming that's our inductive hypothesis, then this will also be true. So here is our inductive hypothesis, and we're going to be assuming that this is true. Suppose that this is true. We have to show that this is true, and notice that this is using k for n. We have to show that this is true for k plus 1. And so if I make that k plus 1, I'm summing from I equals 0 to k plus 1, and I'm putting k plus 1 in here instead of k, so that's going to be r to the k plus 2 minus 1. Okay, so here we go. We'll start with piece of k plus 1, and we'll say, oh, that's really just adding up the first k plus 1 terms, and then we're adding r to the k plus 1. But this one right here, by my inductive hypothesis, is this plus this. Again, I'm going to get a common denominator. Now the common denominator has to be r minus 1, so I'm going to multiply top and bottom here by r minus 1, and that's what I get here. Now, what happens is when I do some algebra on this, you see, this is the same thing. Here is r. We have a common denominator, so what we will do is just add this numerator. So that will be r to the k plus 1 minus 1 plus r to the k plus 2 minus r to the k plus 1, because you see that was being multiplied through, so I distribute and I get this. But then this term will cancel with that term, and I have r to the k plus 2 minus 1 all over r minus 1, which is exactly this, and that's the same thing then as this. So you see we have completed this proof by mathematical induction. We showed that P of 0 was true, and we showed that this, if we assume our inductive hypothesis, then pk plus 1 is true. Let's apply the formula for a sum of geometric sequence, which you should also commit to memory. And suppose m is an integer that is greater than or equal to 3 in this these two examples. So there's two problems. Calculate this sum and calculate this sum. You know what to do. Let's see how you did. Okay, here the r in our formula is 3. So this is going to be 3, and it goes up to m minus 2, so that is going to be m minus 2 plus 1 minus 1 all over this. And when I simplify this, this is going to be m minus 2 plus 1 is m minus 1, and so this is what I get from my simplification. Here, I'm starting at 3 squared, but all of these terms have a factor greater than or equal to 3 squared. So I will factor 3 squared out of this sum. So that's going to be 3 squared, and what is left is exactly what I evaluated in A. So this is going to be 9 times this expression. In closing, and you see this does need some thought, you need to think about these things and read your textbook. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless y'all.